And good evening, AP Physics students. Mr. Gerson coming at you here. Congratulations, physicists. We've made it halfway through our study of electricity and magnetism. We've been studying electricity and electric fields, and now we're moving on to magnetism. Oh, good stuff, good stuff. So let's talk about magnetism. Electricity ultimately comes from charges, electrons, protons, that type of thing. Well, magnetism deals with poles instead of charges. Well, what is a pole? Well, we're not really sure, but we do know that if you take certain materials like iron and have them come out of the earth a certain way, that certain ends of them, like poles, will repel each other, and opposite poles will attract each other. So physicists started calling these things north poles and south poles, and of course that deals with the north and south pole of the earth. Now, magnetic fields are measured in Teslas. There's also a new electric car called a Tesla. There was a band in the 80s called Tesla also. But magnetic fields are measured in Tesla. Tesla is a big magnetic field. Need a really big magnet to get a Tesla. Okay, there's some other SI units called Gauss and that type of thing. So one way we can illustrate magnetic fields is with magnetic field lines. And magnetic field lines look just like this. They point away from north poles, they point toward south poles, and they always occur in loops. That is, you can't have a north pole without a south pole. So they will always occur in loops, and the more magnetic field lines you have in an area, the stronger the magnetic field is there. Whenever you have a north pole, you have a south pole. If you break a magnet in half, you get a north and south. If you break it in half, you get a north and south again. And you can keep breaking them apart until you get down to one atom. So, magnetic fields, well, what do they do besides just, holding things onto our refrigerators, right? You got an A on your last physics quiz, put it on the fridge with a magnet, right? Okay, well, what else do they do? Well, as it turns out, if you have a current running through a magnetic field, there will be a force exerted on it, a force due to the magnetic field on that current. And the force will depend upon the strength of the magnetic field, how long the wire is, what the current is, and the orientation angle between the magnetic field and the current. And I am not going to attempt to draw a picture of this for you. I am going to use our book here, okay? So we're going to practice this some in class, but this is our first true trek into 3 dimensions. So as it turns out, the force experienced by a current-carrying wire when it is in the region of a magnetic field is 3-dimensional. And the way you figure out the direction of the force, this is called the right-hand rule, you put your hand in the direction the current is going. If you're watching this video, put down your pencil right now and use your hand and follow along here. Stretch first. Ooh, don't want to pull a hammy. All right, put your hand in the direction the current is flowing. Curl your fingers towards the direction of the magnetic field, and then your thumb will point in the direction of the force on the current-carrying wire. Okay, that's called the right-hand rule because it gets a little complicated because the force, the magnetic field, and the current are all 3 mutually perpendicular. But they follow the right-hand rule, not the left-hand rule. So anyway, that's how you tell the direction that the force on a magnetic field would exert on a current-carrying wire. But the problem we want to solve is not about a current-carrying wire, it's about an alpha particle. And as it turns out, all of these particles, all of these electrons that are flowing in a current, they experience forces as well. And any charged particle actually experiences a force. So whenever you have a charge that is moving in a magnetic field, that charge will experience a force based upon these things: the charge, the speed of the charge, the magnetic field strength, and the angle between the direction the charge is moving and the magnetic field. Okay? Well, let's dive in and do an example of this here. Okay? Number 9 states the following. Let's say I'm in a region of space and there's a magnetic field. Okay? Now, here is something new. Okay? I'm going to draw the magnetic field coming out of the page. So, this is new stuff. This is a vector pointing out of the page. So, not this way, but this way. Okay? So this symbol here means vector out of page. Okay? If I draw a vector like this, this means into page. Okay? So this means this. This means this going down into the page. Ooh, look, my pen looks just like it. Alright? I always think of a bow and arrow. Like if someone shot an arrow at you, this is what you'd see. If you shot an arrow away from you, this is what you'd see, right? You'd see the little feathers flying away. Hopefully no one's shooting arrows at you, but anyway. So I'm in a region of space where there's a magnetic field, and the magnetic field is pointing out of the page. I have an alpha particle, which has a charge plus 2e, that moving with speed v, and it enters the magnetic field. Now, as it turns out, there's going to be a force due to the magnetic field on the charge, and to find the direction of the force, I use the right-hand rule, which states, put your hand, right hand, not left, right hand in the direction the charge is moving, curl your fingers in the direction of the magnetic field while the magnetic field's coming out of the page, so I would have to do that because my fingers only bend one way, and then your thumb will point in the direction of the force. So as this charge moves this way, it will experience a force this way. And what will happen is, because of that force, it will start to curve like this. Well, now, it's now moving this way, okay? And if it's moving this way and the magnetic field is still out of the page, it will experience a force this way, okay? And as it turns out, it will go in a complete circle like this because the force will always be perpendicular. The force due to the magnetic field will always be perpendicular to the velocity. All right? And in this case, the angle between V and B is 90 degrees because the velocity is all in this plane and the magnetic field's coming out of the page. So, the question is if the radius is 0.025 meters, how big of a magnetic field will I have? And here's how I'm going to solve this problem. I'm going to state that since this guy is moving in a circle, there's a centripetal force acting on it, and that centripetal force is equal to the magnetic field strength. Therefore, mv squared over r, the centripetal force, is equal to qvb. All right, sine theta here is 90 degrees, or is just 1. So if I solve this for b, in the problem they give us everything here except b. All right, I'm going to rearrange this here, do a little algebra, and states that b is equal to mv over qr. Okay. And in the problem, they give us, I didn't plan my space here very well, they give us the mass of the alpha particle, 6.67 times 10 to the minus 27th kilograms. They give us the velocity, 1.6 times 10 to the 7th meters per second. They give us the charge, plus 2, so 2 times 1.6 times 10 to the minus 19th. And they give us the radius r here, that the particle is traveling in a circle in. And if I plug all that in and solve for the strength of the magnetic field, I get 1.3 Teslas as my answer. So a magnetic field of 1.3 Tesla would make an alpha particle of charge plus 2e that is moving at 1.6 times 10 to the 7th meters per second, move in a circle of radius 0.25 meters. All right, nice work, physics students, for your cool information today. I've got something cool for you. 2 stories in Sunday's newspaper about batteries. Super cool. The wind doesn't always blow in Minnesota, so if you want to use renewable energy, you got to store some of it. And Xcel Energy just got a giant battery back online. I'm going to bring this to class, so if you want to read about it, it's pretty cool reading. Also, another article about batteries, about how greener, cheaper tech could be held back by batteries. Talks about the fires on Boeing 787s due to lithium-ion batteries. So I'm going to bring these articles to school next week. You should check them out. All right, nice work, physics students. We'll see you tomorrow.